Hi, welcome to another edition of Calculus 2. Today we are going to start a new chapter, Vectors and Geometry of Space. So we are going to learn about vectors, space coordinates, dot product, cross product, lines and planes, and all that useful stuff from three-dimensional geometry. Okay, let's start by a simple topic that would be vectors in the plane, or as they sometimes refer to it as vectors in R2. So how do we motivate this topic, vectors? Well, if we go take a look at any of our basic courses in physics or engineering, we see there are at least two types of quantities we deal with. One are called scalars. Scalars are defined by a single real number. Standard examples would be mass, temperature, volume, speed, or electric charge. Then we have vectors. Vectors are indicated by having a magnitude and direction, or being made out of a set of ordered numbers. Examples of vectors are displacement, velocity, acceleration, weight, force, electric or magnetic field. As a matter of notation, pretty much all the mathematics you have done so far centers around scalars. So you see standard notation for that, variables and numbers. For vectors, we are going to have a bit of a problem. In the textbook, most of the vectors are indicated by boldface. Boldface would not be easy to write, but we try. Sometimes they show up with a little arrow on top of their variable name, and that would be perhaps more practical than that one. Once we know what the context is and we know who is a vector and who is a scalar, we might use the same type of variable both ways so that our writing would not be overly crowded. Another notation that we are going to use are these angle brackets. So a vector is going to have several components, in this case two components where we are in the plane. So you start with the left bracket, one number, comma, second number, and then a right bracket. That's going to be another notation that we have. There's still going to be some other notation. We are going to talk about that later on. Now, as a matter of motivating vectors, perhaps the easiest thing to start with is the concept of displacement. The rest of these require a bit more background in physics. We have encountered these topics before, displacement, velocity, and acceleration, but let's go ahead and restart this topic. So the same set of ideas show up in geometry as well. So we start with our standard coordinate plane, and to describe displacement we have a starting point or an initial point and a terminal point. And if we go from initial point to the terminal point, we have a displacement. So this is going to be the initial point and this is the terminal point. Sometimes you might refer to it as a start and end, or some other similar terminology. So when I go through this displacement, I create a displacement vector. If I start at a different place and go through the same displacement, I end up at a different terminal point. For our purposes, these two are going to be considered to be the same vectors. So two vectors are the same if they indicate the same displacement. Now I'm sure that you know from the physics background that sometimes we do care about where a certain vector starts. This distinction shows up mostly in the concept of force. When you're using a lever to raise something or lift a boulder or something, of course you know to apply the force as far away from the object as possible to make it easier on yourself to lift it. In the concepts that we are going to be looking at, that issue does not come in. So for all practical purposes, these two vectors are going to be considered to be same vectors for us. Sometimes this is referred to as being equivalent vectors. So I might consider this vector u and this one v, and I might say u is equal to v, and I might refer to these things as equivalent vectors. So it's not necessary for the vectors to start at the same point, end at the same point, to be the same vectors. It could be actually different. Now, if I have initial point A and a terminal point B, I might refer to my vector as AB with an arrow on top of it. So the arrow, the direction of arrow indicates who is the first and who is the last point. And as we said here, we have the issue that well, we have to actually make this thing bold-faced, but as you notice, it's going to take me a few seconds to make things bold-faced. So if you excuse me, you allow me to just write regular variables, and from the context we have to know that we are talking about the vectors or we are talking about scalars. Okay, there are things we learned about line segments back in introductory geometry. Same issues come up here. Suppose I go from the starting point of here 4 and 3 and 5, 6, 7, 8, 9, 10, 11. Let's make sure I'm not making mistakes. Say this is 11 and 6. Okay. In what ways are we going to refer to the vector uv? One of them is to say I've gone from 4 to 11, so I have a displacement of, so 11 minus 4 is my horizontal displacement, and 6 minus 3 is my vertical displacement. So here my vector u can be described this way, and of course if I simplify it, this becomes 7 and 3. Well, for this displacement we know some standard topics. One is how long is the displacement. The length of it, we are going to show it by putting our vectors and putting in double vertical bars. Okay, so this is going to be the length. Sometimes we refer to this thing as magnitude. And here's a new name, a bit fancier than the other ones. We refer to it as the norm. So what's the norm? That's exactly what you remember from Algebra 1 maybe 4 or 5 years ago, where you apply Pythagorean theorem. So if you have a right triangle and you have sides A and B and a hypotenuse C, you know this most famous formula in mathematics, that the hypotenuse sum of square of the two legs. So here we do the same thing, that is 7 squared plus 3 squared, whatever that happens to be, 49 plus 9, and of course that is square root of 58. So length, magnitude, or norm is shown by this notation. So we are going to have one more notational issue. In a textbook this is perfectly okay for it to type it in this style, but for our formulas it's going to be a bit more crowded, having 5 items written just to indicate the length. For all purposes we can just use the absolute value notation, and we cannot go wrong with that. And in more advanced textbooks they actually use that for norm as well. It's essentially the same thing. So if you allow me, another departure from the textbook notation is that I'll just use one single vertical bar so that our future formulas would not look so crowded. If you have several vectors and we have to put here is a pre-warning. Suppose I want to multiply the length of u with the length of v. That's going to be a little bit hard to look at because of so many vertical bars. So we are going to abbreviate that slightly by writing u times v in this style, and not to be overcrowded by lengthy notation. So another concept you remember from your algebra 1, of course, is the notation of the concept of slope, which you remember as a rise over run. For a vector of two components, this simply refers to the second component divided by the first component. So you remember from in algebra, rise was the difference of the y's, and run was the difference of the x's. So that's perhaps how you started it, and at the end you come to this 3/7 second component divided by the first component. Of course, this is referred to as the component form of the vector. So component form simply means we are listing the movement in the x direction and movement in y direction and so on. We are going to have a bit of an issue with the zero vector. Zero vector, again, we have to show it by boldface, or maybe if we take less time, write it like this. In that context, the zero vector will be a vector that has both of its entries as 0. Let's just refresh our memory in terms of, if I have a point P whose components are P1 and P2, and I have a point Q whose coordinates are Q1 and Q2. So I have such a situation. This is point P, this is point Q, and we are talking about the displacement from P to Q. So PQ is going to be obtained by figuring out the displacement in the x direction. That's going to be Q1 minus P1 and Q2 minus P2. If I want to talk about the length of this, by now we got used to a single bar. It's just a Pythagorean formula, so it's going to be the distance formula you are used to from your basic classes. If you want to take the slope m, or the slope of this thing is going to be Q2 minus P2 over Q1 minus P1. For the slope, so long as the Q's are lined up and P's are lined up, it doesn't matter who you write first and who you write the second. Okay, so that is our distance formula. Next issue up is, well, once we know what the vectors are, what are we going to do with them? Well, whatever we do in the rest of mathematics, we do here as well, which is addition, subtraction, multiplication, and so on. Certain operations are going to be a lot more involved than before. As you expect, there are multiple components here to a vector, so there is much more leeway in terms of what we can do with them. So the topic becomes gradually more complicated, and you need to practice a lot to make sure you adopt this language quickly. First issue, so what do we do with vectors? We want to talk about vector operations, or arithmetical vectors. So vector operations, or if you wish, arithmetic with vectors. So we are going to start a topic here that you're going to continue in Calculus 3 and then your linear algebra class. Essentially, you have to redo all of mathematics you have learned for these vectors, and then there are other things called matrices that comes up next. What was the mathematics you have learned? You have learned about addition, subtraction, multiplication, division, exponentiation, and functions. So everything you have done so far, there are just numbers involved here. The question is, what are we going to do if you want to apply these things to vectors and then later on to matrices? So let's start with the simplest of these things. So what's a vector sum? Well, the operation itself is very simple. The concept, however, is much more profound, and you need some background in your physics classes or engineering classes to appreciate what is involved. Mathematical operation, we said, is just as trivial as what you did in elementary school. Suppose I have a vector 2, 3. Let's call that the vector t, and another vector, say r, 5 and 4. Let's make this thing maybe 6. Well, what is t plus r? Very simple. You add up the first component, you add up the second component, and nothing other than that. 2 plus 5 and 3 plus 6. Well, of course, it's going to be 7 and 9. So this type of operation, we call it component wise. Which simply means first with first, second with second, and so on. But what does this mean? Remember, we said we can think about vectors as displacements, and simplest way to understand the vector sum is in terms of displacement. If I have a vector, I'm just going to draw this thing quickly without paying attention to see if it's the right scale and such. If I have vector t and some other vector r here, how do I add them up? We said we can move the vectors around and it still will be the same vector, so we choose some base of operation. Maybe I come some arbitrary location here and duplicate my t. Here's my t. So parallel to that, same kind of displacement. Then maybe I color this thing differently so that we can follow this thing better. I start my second vector where the first one finished, so here I will draw my r. So the result of this sum, let's call it w. The result of this sum is what takes me from the starting point to the final point. Why? Well, I'm making a horizontal displacement followed by the next horizontal displacement. So that is what 2 plus 5 refers to. That's the net displacement for w. And then a vertical displacement and another vertical displacement. I'm adding them up to find out the vertical displacement of w. So that is what the vector sum refers to. Now, when you take your physics classes, you do this by having some weights that create forces for you, and then you add the forces to see if the forces actually add themselves up in this style. So there's a mathematical operation, and then there is a physical reality, and you want to see that these two are actually the same thing. Next operation that we have in mind is a so-called scalar multiple. Scalar multiple So suppose I want to talk about 4t. So remember, t up there was 2 and 3. And who is 4t? Well, 4 times each component. So 4 times 2 and 4 times 3. As simple as that. So that's 8 and 12. So if I have a vector, this is vector t, and then I stretch it by a certain multiple, so here's a second 2t, this is 3t, and then up to here. So this whole thing from beginning to end, this whole thing is going to be 4t. So stretching a vector is shown by scalar multiple. Well, what if I multiply by negative number? So what is minus t? Well, minus t would be minus 1 times 2, 3, and of course that is just minus 2 minus 3. How do you understand this thing geometrically? If I have a vector t, now we have two ways of doing this thing. One is start from the same point and just go in the opposite direction. So that's one way of getting minus t. Another way of getting minus t is to flip the heads and tails of the vector that you have. So this is another common way of making a minus t. You have to be comfortable with both of these things to operate quickly in other contexts. So that is scalar multiple. This is a negative of a vector. Negative of a vector, simply you are flipping its direction, but otherwise it stays the same. Next topic up, well, we did addition, vector sum. How about vector subtraction? Or vector difference. So suppose I have a vector t and I want to subtract r from it. Well, exactly like elementary mathematics. You can think about this thing as t to which you're adding the negative of the vector r. Okay, that's one way to think about it. Another way is simply, let's go write this 2, 3, 5, 6. So t was 2, 3, and r was 5 and 6. So t minus r, this is also component wise operation. 2 minus 5 and 3 minus 6, and that is minus 3, 3 and yes, minus 3 and minus 3. So now in picture, this is going to be a little bit more involved than what we had before. Suppose again I have a vector t here and another vector r, and I want to figure out their subtraction, t minus r. Two ways of doing this thing. First, let's go ahead and draw them from the same point. So suppose this is a copy of my t, this is another copy of my r. Think about it as t minus r, as t plus minus r. I can take my r and flip it by going in the opposite direction. So this becomes minus r. Now, adding t and minus r, we can do it by making our construction that we had here before, t followed by r, or r followed by t. Here we do the same thing. I can do t followed by minus r, or I can do minus r followed by t. Either way, I come to this location. So this is going to be t minus r. So I flipped r to this location, and then I added t and r to arrive at this. Now we said we have a second option, which is take the vector that you want to negate. You can exchange its heads and tails. So what we do here is to take this and flip the direction of it in the same spot. So this by now becomes minus r as well, just like this red one. Now, another way of thinking about this thing, this is minus r plus t. That is, I can follow this green followed by this black. So what I get is this vector. So minus r plus t is same as t minus r. So this edge of this parallelogram and this one are the same thing. So when it comes to subtraction of the two vectors, you need to practice it in a few diagrams to become comfortable with the operations. Now, it's easy to verify with respect to the kind of operations we detailed that certain mathematical properties we are used to in high school are still valid. These are typically listed as properties or axioms of vector operations. So properties of vector operations many of the properties you're familiar with are still here. If I have a vector and another vector, I can add them in either order and the result will be the same. So this is called commutative property. So again, remember, I'm either supposed to write them in bold or put arrows on top of them, but again, to avoid the clutter, we are not doing that. Another operation you remember from, another property you remember from high school classes is this one. That if I have three vectors and I want to add them, it doesn't matter how, I'm going to list them in my addition, and this one is referred to associative property of addition. Then we said we have a zero vector, which is very much like the zero we had for scalars. If you add them to any vector, it does not make a difference. So that is sometimes referred to null element or identity element. Each vector has, if you wish, a sister vector or brother vector that's called the negative of that vector. If you add them, you get zero. Let's emphasize here, this is the zero vector, not a single zero. Rather, it's a list of zeros, zero displacement. Then we have some properties for multiplication. You remember that if I have A plus B times C, we had certain associative, certain distributive property. Here, slightly different tone to this thing, because now these are scalars. So this is a scalar, it's just a number. This is a scalar, and in this notation, this is supposed to be a vector. So to be correct, I have to put an arrow on top of this thing. Let's do that here. So what does this mean? This is A times U plus B times U. Or what is this thing saying? It's saying that if you have 2 plus 3 times some vector U, you could also think about it as 2 times U plus 3 times U. With respect to displacement, this is just like a trivial statement to make. But the interesting fact is that there are two types of distributive property. One we are distributing over scalars, and another one distributing over the vectors. What does that mean? If I have A times U plus V, again, let me put the arrows on these things so it's clear who's who. This is same as A times U plus B, A times V. So what does this mean? If I have, I'm doubling U plus V, the same as doubling U first and doubling V next, and then adding them up later on. We have an associative property for multiplication as well. If I have a number times another number times a vector, that is same as taking my vector, multiplying by one of these things first and multiplying by the other one next. So you notice all of these things are related to order of operation, and what we are saying is that we are safe in these cases, that order of operation does not matter. There is one assumption that looks rather strange to students to see it, and that is, if I take a scalar number 1 and multiply it by a vector, I have to assume that I'm going to get that vector back. If that property intrigues you, well, you're going to see more of that in an advanced class called advanced algebra or linear algebra later on, but right now we leave it as that. Then there is another property that also is a bit hard, on one hand trivial, on the other hand rather hard to swallow, is that if I take the scalar 0 and multiply by a vector u, what do you think I'm going to get? Well, so 0, suppose I multiply it by vector 2, 3. Well, what's going to happen? Well, of course, I get 0, 0, which is my 0 vector. So this is 0 vector. This one gets to be proven and demonstrated, even though it looks rather trivial, but in your future classes you're going to actually prove that. Okay, these are some of the standard properties that come naturally, and you're not going to spend much time on it. The one item I forgot to mention in connection to what you're going to do in your physics classes, the very simplest operation, vector sum. In your physics classes you are going to refer to this as a resultant. Resultant force is sum of two forces, and I just wanted to mention that you might be able to detect that in your physics classes as well. Okay, so basic operation. Fortunately, so far there wasn't anything out of the ordinary. Let's go ahead and list some other properties of vectors. If I have a vector, if I double it and then find the length of it, what do you think I'm going to get? Well, I'm going to get the same thing that if I take the length of the vector and then double it later. Okay, so that's not a big surprise. If you stretch a vector until it's twice as long as it was before, well, the length of it is going to double. Well, what if I take the vector, multiply it by -2, and then measure the length of it? But the length is always a positive number. It's going to turn out to be just number 2 times the length of the original vector v itself. To capture both of these things in a single formula, we say if you have a vector, multiply it by some number. That number could be positive or negative, and then measure the length of it. What you're going to get is the length of the original vector, but now you have to multiply by absolute value of the number that you had. So you are going to see this kind of formula in a basic calculus text, perhaps in this style. We said they put a double vertical bar for this one, so they put the double vertical bar for v, and for absolute value they use a single bar. Okay, not a big difference. Again, we said we are doing this thing because having so many vertical bars is going to be hard to look at. Next topic up that comes up, so we are going to go through a list of mini topics and just getting used to the notation and terminology. Next topic up is the topic of unit vectors. Well, as the name implies, unit vectors that are of length 1. So these are vectors of length 1. Well, sometimes we have a vector of arbitrary length, but we want to find a vector of length 1 in direction of this vector, essentially cutting it to size. So for example, perhaps this is the vector that I want. So suppose I have a vector A and I want to find the vector u. Typically unit vectors are shown by letter u or something. So say given an arbitrary vector A, find the unit vector u in direction of A. Well, it's very simple. If you have A and it is, say, 4 units long, well, divide it by 4 and then you're going to get u. So what you need to do is to find out first of all how long A is and then divide by that length. So it's very simple. You take the vector A, divide it by how long it is. How long it is, we said shown it this way, and that's going to be our unit vector u. Of course, A cannot be 0 because then you'll be dividing by 0. Other than that, we have no problem. So suppose, here let's take a simple example. Suppose A is vector 3, 4. First of all, how long is A? Well, you apply the Pythagorean formula, 3 squared plus 4 squared. So you know from long ago, this is a lucky coincidence of this becoming a whole number. So A divided by length of A means 3, 4 divided by 5. It's typically written like this, that is, you divide through by 3/5 and 4/5, or you can leave it outside. So this is another alternative for writing it. Either way, this is perhaps cleaner to write it by factoring it outside. So that's a unit vector in direction of a vector. And we have special unit vectors. Special unit vectors line up with our axes. So if I have x coordinates, x-axis and y-axis, I can think about the unit vector in this direction, and I can think about the unit vector in that direction. These are going to be special vectors for us. We are going to refer to them as I and j. And again, remember, this is really either has to be a bold face I, or I like this. Sometimes they write it I like that in textbooks, just to make sure it stands out. So here, so again, I have to make this thing boldface or put some little decoration on it to warn the reader that this is a vector, not just a number. Well, what is the vector I? Vector I going in the x direction is 0, 1. Who is vector j? This is having no x component, but its y component is 1. So these are special unit vectors, sometimes referred to as standard unit vectors. Of course, if you take all the unit vectors that start from same place and you draw all of them, what are you going to get? What does this look like? The tips is going to make the unit circle for us. So unit circle, the word unit appears there as well, is the same idea. Okay, next we have a major concept that is going to be mentioned briefly here, and then in your advanced classes this is going to show up in much more profound way. It's so-called triangle inequality. This is also something that you have encountered in your elementary geometry classes in high school or in physics classes. Well, how does it show itself there? If I have a triangle, you intuitively sense that this leg is shorter than some of those two. In other words, you say the straight path is the shortest distance between 2 points. What we are saying is that if I have a triangle with sides A, B, C, then A is less than B plus C. And same thing applies to all of them. B is less than A plus C, and C is less than A plus B, and so on. Triangle inequality refers to this. Well, if I had a vector u and then followed that by a vector v, what I get is the sum of these two vectors, which we write u plus v. If we capture the same idea here, what we are saying is that length of the sum is less than sum of the length. Well, in some circumstances they'll become exactly the same. What case is that? Can you pause for a second and tell me under what situation would they be actually equal? So pause this thing for a second and think about special case. In what special case is it that when I add u plus v, the length is a sum of the original two. Well, of course, if I have u and the v is in extension of u in the same direction as u, then u plus v, this vector, will have the same length as the sum of those two. So this is a triangle inequality. Is a very fundamental concept. That is what we expect from a notion of a distance to have this property. So if somebody wants to come up with a new fangled style of measuring distances, the first litmus test is that it should pass the triangle inequality check. Now we're just going to practice with a bunch of very tiny problems. So in this section the topic is substantially simpler than the stuff that we had before, but it's important to get used to the language so that you can build on that and you go further. So do as many problems as you can, open your textbook and try to do a speed testing for yourself, essentially 20 problems in 20 minutes or something, even less than that. Okay, so one of the concepts that we have here is connecting vectors to angles. So if I have a vector u and I'm drawing this thing in the standard coordinate plane starting from the origin, well, I can think about this as making an angle theta. Well, if I make a triangle here, what are these two lengths? So we are making standard connection to basic trigonometry. So let's go back here, quick review of trigonometry. If I have a right triangle and this is A and this is B and this is C and this is the angle theta, well, how is cosine of theta defined? Ratio of adjacent to the hypotenuse. So adjacent is the hypotenuse times cosine of theta. So in this case this one is going to be the length of the vector u times the cosine of the angle theta, and this one is going to be same approach here. You remember sine of theta is the opposite over the hypotenuse, so opposite is going to be hypotenuse times sine of theta. So this blue portion is going to be the length of u will be the hypotenuse times sine of theta. So you can take the vector u and show it like this, is the length of u times cosine of theta, comma, the length of u times sine of theta. To make this thing look nicer, we can factor the length, put it outside and say it's cosine of theta, comma, sine of theta. So that's going to be the vector u. If u happens to be unit vector, well, the length of it will be 1, and this will be showing just as cosine and sine. That is one way of describing a vector. Remember, we still have another option, which is taking this thing and showing it with the unit vectors that we had, I and j. So these are the let's put the arrows on top of them. Sorry. So you remember I was the vector that was in the x-axis direction, and that was what, 1 and 0, huh? J, who was j? J was going in the y direction, and who was j? J was 0 and 1. So that's another way of writing the same thing. Okay, and then you are going to have many examples of these things when it comes to your basic physics classes with respect to velocities and forces and so on, which I leave to those classes. So remember, from this section you want to do several dozen problems. Each of them should take less than half a minute for you. and essentially you need to do speed check for yourself. Okay, until our next lecture, which we are going to take a look at the same thing in 3 dimension. Good luck and God bless.